Hi everyone. Welcome to the next talk. Priyanka Mukhopadhyay will be talking to us about optimizing Clifford+T circuits. So Priyanka, you can take it away.
Thank you. Thank you, Julian. Hello, everybody. Greetings from Waterloo, Canada. First of all, I'd like to thank the organizers for organizing this nice workshop. So I'm Priyanka, and today I'll be talking about a polynomial time and space heuristic algorithm for T-count. This work has been done with Michele Mosca at University of Waterloo. So this is the overview of my talk. I'll briefly introduce some definitions. Then I'll talk about channel representations because our algorithm works with the channel representation of unitaries. Then I'll describe an exponential complexity provable algorithm and a polynomial complexity heuristic algorithm. So I'll quickly go through the introduction part because I'm sure, I think many of you know all these things. So today I'll be talking about quantum circuit synthesis algorithm. So in a quantum circuit synthesis algorithm, the input is a n cross n unitary, where n is exponential in the number of qubits. And throughout my talk, when I'll be talking about the complexity of algorithm, I'll give the complexity as a function of the input size. And in this case, the input size is this capital N, which is itself exponential in the number of qubits. And the goal of a quantum circuit synthesis algorithm is to give a decomposition of the unitary into a sequence of gates. And each of these gates are themselves some unitaries. And these gates belong to a universal set. And we have an added task like the optimization of certain cost function, like the number of a particular gate. Now, suppose this is the decomposition from a quantum circuit synthesis algorithm, and U dash is the unitary which is actually implemented by the gates in the decomposition. That is, U dash is the product of the gates which we obtain from this decomposition. Then depending upon U dash, there are two kinds of quantum circuit synthesis algorithm. One is an approximate synthesis algorithm, where U dash is not exactly equal to U, but it's close to U, like the distance between U dash and U is at most some epsilon. And then we have exact synthesis algorithm, where U dash is equal to U up to some global phase. And it has been proved by Giles and Selinger, if U is exactly synthesizable on a quantum circuit, then its entries belong to the ring Zi 1 by root 2. At most, one ancilla is sufficient. And if certain conditions are satisfied, then we do not require any ancilla. So as I said, these gates, we require these gates to belong to some instruction set, which is usually a universal set. So a quick recap, a universal set is a gate set which helps us to approximate any unitary operation to arbitrary accuracy by a quantum circuit, which involves gates from this set. For example, Clifford+T is a very popular universal gate set. So let's look at what a Clifford+T gate set is. Before that, n-qubit Pauli operators are tensor product of single qubit Pauli operators, and these are like X, Y, and Z gates. The n-qubit Clifford operators, they belong to the group generated by the Hadamard gate, the phase gate, and the C0 gate. And the n-qubit Clifford+T operator, they belong to the group generated by the Hadamard gate, the T gate, and the C0 gate. So this is the relation. The Pauli operators are a subset of the Clifford operators, which are a subset of the Clifford+T operators. So as I said, the Clifford+T operators, they belong to a universal gate set. And they are also a fault-tolerant gate set. Now, what does a fault-tolerant mean? So they have a fault-tolerant construction in most error correction schemes. And this is required to deal with errors due to noise on quantum information for faulty quantum gates, faulty quantum state preparation, and faulty measurements. And this becomes very significant for long computations. So, for the Clifford+T operators, in most error correction schemes, there exists transversal implementation of the Clifford group gates. For example, this is a transversal C0 implementation between logical qubits encoded with the Steen code. But the non-Clifford gates, like the T gate, they usually require large ancilla factories and additional operators like operations like gate teleportation and state distillation, which are less accurate procedures, and they also require more time and space compared to single physical gate. So this makes them more costly, and thus gives the motivation for studying these kind of problems, because it is important to reduce the number of T gates. So I'll define the T count. So the T count of a unitary is the minimum number of T gates in a Clifford+T circuit that implements this unitary. And this may change with the use of additional ancilla qubits, measurements with classically controlled operations. So let's define the problem count T. In the optimization version, we are given a unitary, and our task is to determine the T count of this unitary. And in the decision version, we are given this unitary and a natural number m, and we have to decide if the T count is at most m. And it has been proved by Gossett, Kloshnikov, Mosca, and Ruscio that if we can solve count T, then we can get a T-optimal circuit for this unitary with overhead at most polynomial in the T count of U and the dimension of U. So now I'll talk about channel representation, because both our algorithms work with the channel representation of unitaries. Now, given n cross n unitary, its channel representation is an n square cross n square matrix with rows and columns which are indexed by n qubit poly operators, and each entry is given by 1 by 2 to the power n trace of PRU, PS, U dagger. And this comes from the fact because the n qubit poly operators is a basis for the space of all Hermitian n cross n matrices. And if U is unitary, its channel representation is unitary. It respects the multiplicative law as well as the tensor product law. And each, its law means it's not a law, it's a rule. That means the channel representation of the product of unitaries is equal to the product of the channel representation of unitaries. And the channel representation of the tensor product of unitaries is equal to the tensor product of the channel representation of the unitaries. And each entry of this channel representation is real. So if U is exactly synthesizable, that is, if its entries belong to this ring Zi1 by root 2, then the entries of its channel representation, they belong to the ring Z1 by root 2. The channel representation of a Clifford operator is very easy to notice because it has only one non-zero entry in each row and column, which is equal to plus minus 1. So it's basically, it permutes the columns with a plus minus 1 sign when applied to any other unitary. So I'll define the smallest denominator exponent because we'll be working with these things. For any non-zero element in Z1 by root 2, the smallest denominator exponent is the smallest natural number k, for which v can be expressed as a plus b root 2 by root 2 whole to the power k. So ST of 0 is 0. And for any matrix, the ST of the matrix is the maximum of the ST of any of its entries. For a Clifford operator, its smallest denominator exponent is 0. And it has been proved by Gossett, Kloshnikov, Mosca, and Ruscio that for a single qubit unitary, the T count of the unitary is equal to the smallest denominator exponent of its channel representation. Now, given any unitary, we know it can be written as an alternating product of Clifford operators and T gates. So we can actually compact this unitary in this form where U is equal to product of the RPJs times some Clifford operator C0. And these RP's expressions, they have this form. And if you're wondering where the T gate is hidden, it's if I expand this expression, there we see the T gate is hidden. So each RP unit has one T gate. So we can write the channel representation of U as a product of the channel representation of the RPs times the channel representation of the Clifford operator. Now, let's look at the structure of the channel representation of these RP units, which has T count 1, because this will help us to give more efficient algorithms, and it also gives us the intuition for the heuristic algorithm. So the diagonal elements in this channel representation of RP are 1 or 1 by root 2, and exactly half of them are 1 by root 2 and half of them are 1. So for example, the channel representation of Yx, so this is the channel representation of Yx. The whole unitary has size 16 cross 16, but it has 8 diagonal entries, which are 1 by root 2 and the rest are 1. And if a diagonal entry is 1, then the rest of the elements in the corresponding row and column is 0. If it is 1 by root 2, there is exactly one position in the row where we can have a 1 by root 2 and a one position in the column where we can have a minus 1 by root 2 or vice versa. And the rest of the elements are 0. For example, so this is the channel representation of yx. So we can see, right, when there is a 1 by root 2 in the diagonal, there is exactly one position in the row where there is a minus 1 by root 2 and one position in the column where there is a 1 by root 2. And so we can see many such patterns in the channel representation of such unitaries. Thus, to store this unitary, it's sufficient if we can store information about these squares. So this n square times n square unitary can be stored as an array of length n square by 4. And in this array, we store pairs of the form j plus minus k, which implies that the diagonal entry, j's diagonal entry is 1 by root 2. And in the jkth entry, it is plus minus 1 by root 2. And from here, we can deduce about the kth row. So no need to store the information about k plus minus plus j entry. So for example, this whole unitary can be represented by this array of length 4. Okay, and these structures have been described in our paper with Michele Mosca. And to compute the inverse of the channel representation of the RPs, we simply flip the sign of the off-diagonal elements. Now let's look what happens when we multiply any matrix by the channel representation of RP. So if the diagonal entry is 1, suppose the ith diagonal entry is 1, what happens, and suppose W is the product of channel representation of RP and V, then what happens is the ith column of W becomes equal to the ith column of V. And if a diagonal entry is 1 by root 2, and suppose the ith diagonal entry is 1 by root 2 and the lth entry is plus minus 1 by root 2, which implies that the lth diagonal entry is 1 by root 2 and the lith entry is minus plus 1 by root 2, then what happens? The ith column and the ith row and the lth row of W becomes just a combination, like the linear combination of the ith and the jth row of V. And the ST of W, it can increase from, and the ST of W, the difference between the ST of W and V is at most 1. So it can be minus 1, 0, or 1. And this is like important for when we derive our heuristic algorithm. And the complexity of this multiplication is order n to the power 4. And this is faster than the currently fastest algorithm for matrix multiplication, which was given by Legal. And the complexity of that algorithm would have been order n to the power 4.7457278. So we give some marginal improvement here. Now, as I said, each entry of the channel representation of U is real. So if U is exactly synthesizable, then its entries in the channel, the channel entries of the channel representation, they belong to the ring Z 1 by root 2. So this gives us an idea about the data structure for U. So if we represent the entries of U by this triple, by this tuple A, B, and K, where A is the rational part, B is the irrational part, K is the denominator exponent, then what happens? We can do all the operations required, addition, subtraction, inverse, multiplication by integer arithmetic. No floating point operations are needed for any of our algorithms. Okay, now I'll describe an exponential complexity provable algorithm. So before that, let's describe some important terms which are relevant for our algorithm. So a coset label of U. So this is just like a representation of the channel representation of unitaries which are exactly synthesizable. So how do we derive it? We rewrite the channel representation such that each non-zero entry has a common denominator, root 2 times SD of the channel representation. For each column, we look at the first non-zero entry. And if the rational part is less than 0 or equal to 0, and the irrational part is less than 0, we multiply the column by -1. Then we permute the columns so that they are ordered lexicographically from left to right. And it has been proved by Gossett, Kalashnikov, and Mosca and Ruscio that if the coset labels of two unitaries, the channel representation of two unitaries are equal, then it implies that U is equal to V times some Clifford up to some global phase. Okay. Now, let's talk about sorted coset database. Now we have calculated the coset labels. Now we want to, and we know how to order them. So we now want to have an ordered database consisting of these labels. So for any k, DKN is a sorted coset database, which consists of channel representation of unitaries such that every unitary in this database has T count k. And for any unitary with T count k, there is a unique unitary in this database with the same coset label. And this database is always sorted according to the coset labels. Okay, so now I'll describe a nested meet in the middle algorithm, which has been developed by me and Mosca. So in the input of this algorithm is an exactly synthesizable unitary and an integer m and c, which gives the label, the level of nestings that we would want in our algorithm. The output is the T count of u. If it is less than m, or we return no. The intuition behind this algorithm that we know that unitary, the channel representation of u can be written as the product of the channel representation of RPJs and the channel representation of C0. So we can search for these channel representation of RPJs such that this condition is satisfied. So first we calculate the channel representation of u and the coset label. Then we pre-compute sorted coset databases up to level m by c. So we start with the identity unitary, and basically we build a tree where with the unitaries of the where we multiply the unitaries of a level by RPs, and we store the products if the coset label is new. Okay, and then we order these unitaries. For example, so this is the construction. This shows the construction of the sorted coset database. We start with identity, we multiply it with RPs. Then with each RPs in the then each RP in the first level we multiply by RP to get the unitaries in the second label. Okay. Then what we do, we check if the T count of this unitary is at most m by c. We have stored all the unitaries of T count at most m by c. So we can check this very efficiently by a binary search because all the unitaries are ordered lexicographically. So if we do not find the unitary in this database, then we do the nested meet in the middle iterations. What we do is basically we take the unitaries at the last level of the tree, and using this we search for any other unitary in the database so that the T count of u is at most say twice m by c. If we do not find it, then we check if it is thrice m by c and so on. Okay, so it will be useful to describe in this diagram. So suppose let's take this unitary W24 in the last level of the database which we have built, and suppose V is WT4 dagger times U, and we find that W11 in the database has the coset label equal to V. Then we can say that the T count of U is the T count of WT24 plus the T count of W11. Okay, and if we do not find till level m, then we say that the T count is more than m. So if C is equal to 2, if we have two levels of nesting, then we get the meet in the middle algorithm, which has been developed by Gosset, Kalashnikov, Mosca, and Rusho. The complexity of our algorithm is as follows. The space complexity is order n to the power twice m by c, polynomial times m and capital N. This m is order the T count of u. And the time complexity is order n to c minus 1 m by c, polynomial in m, some polynomial in m and n. Okay, so this is an exponential complexity provable algorithm. So now I'll describe a polynomial complexity heuristic algorithm. Okay, so the input of this algorithm is a channel representation of a unitary, and the output is the decomposition of this unitary, that is the RPs and the Cliffords, which arrive in the decomposition of the unitary, okay? So the intuition is as follows. We know that this expression that U is equal to the channel representation of U is equal to the product of the channel representation of RPJs times the channel representation of C0. This can be equivalent written in the following form. It is equal to the product of RPJ inverse, the inverse of the RPJ operators, times the channel representation of U is equal to the channel representation of some Clifford. And we know how to check a Clifford. The ST of this unitary will be 0. So we search for this inverse RPJs and try to see like if any combination can satisfy this kind of a relationship. Now, so we build a tree as we did before with channel representation of U in the root, and then we try to prune the tree. To prune the tree, we develop some divide and select rules. So what happens at each level, we group the nodes according to some properties or parameters. So these properties or parameters are such that we hope that they will distinguish the correct unitaries, that is the unitaries which come in the minimal decomposition of U from the incorrect ones, okay? And then we try to select the group with the minimum cardinality. So we have selected two properties. One is the change in STE, the smallest denominator exponent, and Hamming weight. Here by Hamming weight of a matrix, I mean the number of non-zero entries in a matrix. Okay, so for STE, I said like the intuition is very simple. When we multiply a unitary by the channel representation of RP, what happens is the STE changes by at most 1. Either it increases by 1, decreases by 1, or remains unchanged. Now, what happens when we build the unitary from identity? Mostly the STE increases and sometimes the STE decreases. And it is similar kind of characteristic is noticed for the Hamming weight. Now what happens, so what we do is we try to do the inverse operators and we hope that this will distinguish the correct unitary. So what happens is, suppose we have a unitary U and we multiply by some RP1, then we see the STE has increased. Now when we multiply by the inverse of RP1, so obviously the STE will decrease. Now, if that product unitary, if we multiply by the inverse of the other RPs, then what we hope is most of them will give me the opposite trend. So there are 3 divide and select rules which we have developed. First is a very coarse rule in which we have 2 subsets. We divide the nodes in 2 subsets, S0 and S1. So in the first, we store those unitaries for which for which the ST increases, and the second, we store those unitaries or nodes in the tree for which the ST has decreased. And when the ST doesn't change, that is, we cannot decide, we place them in both the sets. Then we select the set with the minimum cardinality such that ST is at most M dash. I'll explain later where this M dash comes from. In the second rule, we divide the nodes into 4 sets. So we first place the unitaries according to the change in the ST and the Hamming weight, according to the increase and decrease of the ST and the Hamming weight. If the Hamming weight remains unchanged, we place them according to the change in ST. So we give more priority to the STs. And when the ST is unchanged, we place them in all the nodes, in all the sets. That is, we always select those nodes. Again, we select the set with minimum cardinality such that ST is at most M dash. In the third rule, we divide the nodes into 9 sets according to the increase, decrease, or unchanged characteristic of the ST and the Hamming weight. Again, we select the set with the minimum cardinality is such that ST is at most M dash. Okay. Now, in the heuristic algorithm, so we first check whether we can have a decomposition of length M. We know we cannot have a decomposition less than M, where M is the T count of, or the ST of the channel representation, because we know the ST can decrease by at most 1. So to reach a Clifford to 0, it must need at least M steps. So to check that, which is basically the iterations 2.1, the loop 2.1, we multiply each node in some level by RP inverse, then we note the change in ST in Hamming weight. And if we reach a Clifford, then we stop and return the path. Else we apply the divide and select rules with M dash M minus 1. This M dash comes from the fact that there are M dash levels left in the tree. So you have to, if we have to reach a Clifford, we have to reach within M dash steps. Okay, then the selected nodes became parents for the next level. Now, if we cannot find any decomposition, then we try to check if a decomposition exists of length m+1 and so on. So this 2.1 iteration, this loop looks as follows. So we start with the channel representation of U. We multiply by the RP inverses. Then we divide and select. Suppose we selected 2 nodes. Then we again multiply them by the RP inverses, okay? Then we again divide and select. Suppose this time only 1 node got selected. Again, we multiply by RP inverse. And this time we see we reached a Clifford. We can check it because the ST of this unitary will be 0. Then we stop. And we return the path which we obtain in this way. This gives the decomposition. So if this is the path, these are the RPs, then your U can be written as the product of these RPs times C0 up to some global phase. And our conjecture is the set of nodes which have been selected by these divide and select rules, they always include the correct nodes. That is, they have that these nodes occur, or these unitaries in those nodes, they occur in a minimal decomposition of the channel representation of U. And the cardinality is always polynomial in capital N. Okay, so the tree is always bounded in size. So this gives the space and time complexity of our algorithm as some polynomial in capital N and the T count of U, because we need so many iterations. Now we have synthesized some circuits, some benchmark circuits, as well as some random circuits. So first I show the comparison with the parallel algorithm, which has been developed by Olivier Di Matteo and Michele Mosca. So currently what we checked is this is the fast, before our work, this was the fastest, which was a parallelized version of basically the algorithm by Gosset, Klasnikov, Mosca, and Russo. So this is a parallel, so they had a parallel algorithm, they used 4,096 cores. We used only 1 core, our algorithm is serial. So the largest unitary which they could synthesize was the 1-bit full adder. And this took time 12.5 hours in their algorithm with 4,096 cores. We could synthesize this adder with in time 429.17 seconds, which is a little more than 7 minutes, using only 1 core. And we also could synthesize some bigger unitaries. These unitaries we obtained from some previous papers, and we received much lesser, and we obtained much lesser T count as compared to the previous best results, for example, by using T-par. Which is an algorithm by Amy, Mashlov, and Mosca. So we also synthesized some random circuits. So some 2, 3, and 4 qubit random circuits. We started with the number of T gates, 10, 20, 30, 40, and these circuits, we took 10 circuits in each group. And this column reduced means we saw that in the circuit which has been synthesized by our algorithm, the number of T gates is much less than the input number of T gates. Obviously, we couldn't verify whether this is the minimum or not, because no current existing algorithm can synthesize such big circuits. This number of nodes, this means like the maximum number of nodes that accumulates at any level in the trees that we have built, that gets built during the algorithm. So this shows like the extent of pruning that our algorithm achieves. And this is the average time and the standard deviation of the circuits which have been synthesized by us. Okay, so now let's summarize. So to summarize my talk, so we studied in our paper the channel representation of unitaries, which helped especially the channel representation of RP units, which helped us to obtain more efficient algorithms for multiplication, inverse, etc. And all these operations could be done by integer arithmetic. Then we obtained space-time trade-offs for meet-in-the-middle type of algorithms. So we basically developed a nested meet-in-the-middle algorithm, which helped us obtain the space-time trade-off. And these are like provable exponential complexity algorithms. And we also described a polynomial complexity heuristic algorithm. Thank you.
Thank you, Priyanka. Can you hear me?
Yes, I can hear you.
Okay, so there are 2 questions in the Slack channel that maybe I will relay right away. So as best I can. So the first question is from Harney, and he's basically asking if you could clarify essentially what you mean by T count. So his question is, you define the T count as the minimum number of T gates. What do you mean by minimum in this context?
Oh, by minimum means, look, when we synthesize a unitary, there can be many circuits for the same unitary, right? So
Right.
by minimum means like the among all the circuits, like whichever circuit has the minimum number of T gates. Like we cannot, for example, a Toffoli, we cannot have any circuit which uses less than 7 T gates without any ancilla or any other distillation on all these processes. So by minimum means among all the circuits that can synthesize this unitary, the circuit which has the minimum number of T gates.
Got it. Okay. Yeah, I think that's clear. So, and the second question is from John. So he's asking about the sort of complexity theoretic consequences of basically having good algorithms to compute the T count. So here's his question. He says, calculating the exact T count is co-QMA hard. So knowing that, how close is your algorithm to having weird, complexity class implications, like maybe some kind of collapse of certain complexity classes or something like that? And
Okay.
another way of formulating the question, which John also states here, is how much can we still expect the provable algorithm, at least, to be improved? Do you have any sense of this?
Yes. So the thing is like, so there is some information theoretic lower bound for the synthesis of exact unitaries. I think it is at least 3 to the power small n, where small n is the number of qubits. Okay. So the thing is, we cannot hope to get anything less than that. Our algorithm is polynomial in capital N, where capital N is 2 to the power n. So it really doesn't violate any complexity theoretic results that we have so far. We can at best improve the polynomial in capital N. For example, we know the lower bound is 3 to the power n something. So we can at most say we can have a better polynomial, but it doesn't violate the existing results. And we have this complexity of using Reed-Muller codes. This was a paper by Amy and Mosca. So we really cannot hope to go below that 3 to the power n or something bound. I do not remember exactly. So so I think this I think this answers the question. So it really doesn't collapse any class or anything. It really respects all the complexity results that have been derived so far.
Got it. Okay, thank you very much. Thanks a lot for the great talk. And you should join the Slack channel. Maybe there's going to be further discussion in there.
Okay, thank you so much.
Bye, Priyanka.
Bye.